So, Dr. Deepak, you can see around 170 participants are there in this particular platform, and for other people also, we are recording it live streaming on YouTube.
Yes, I don't have any problem.
Yes, your screen is visible.
Yeah.
Fine. It is perfectly fine. So, participants, it is my pleasure to introduce you to Dr. Deepak Ranjan Naik. He is an eminent faculty member of Department of Computer Science of our institute, MNIT Jaipur. Prior to joining MNIT Jaipur, he has also experience at NIT Surat and IIIT DM Kanchipuram as a faculty member. He has very vast experience in the area of image processing, and he has applied several tools on various application of image processing. And Dr. Deepak has a large number of publications to his credential, starting from various IEEE transactions to the top quality conferences all around the world he has cracked. He and his research groups are doing very good over here in MNIT. And over to you, Dr. Deepak, for today's session. Dr. Deepak, we cannot able to listen you.
Okay. Yes. Am I audible right now?
Yes, now you are audible.
I think participants have already joined, right? So we'll start at
Yes.
6:20, right? I think there are 4 minutes left.
No, you can start right now also. There is no hard sound
Then.
about it. Yes.
Okay.
So in this platform, actually, participants won't directly communicate with you.
Okay.
By unmuting, each option is not there.
Okay.
So participants will communicate with you over chat.
Okay. I'll go through it. I'll go through it at the end of the lecture, and also
Yes,
have share my. I think this is my email ID, which is I intentionally I put it on my slide so that they can, if any doubt they are having, they can also share their doubts over the email. Okay.
Sure.
Thank you. Okay. So good evening to all, and the title which I have chosen for this lecture is Application of Advanced Optimization Algorithms to Image Processing. So in this particular session, I will be focusing on how the meta-heuristic optimization algorithms, which is the main theme of this particular course, is been applied to image processing applications ranging from image enhancement, segmentation, feature extraction from the images, and most importantly, how these meta-heuristic algorithms have been applied to the most powerful and popular architecture of deep learning known as convolutional neural network. So before I start, discussing about the applications and how these algorithms are being applied to different kind of image processing applications, I'll just give an overview of meta-heuristic optimization algorithms, and I'll just take only 1 to 2 minutes because already the experts have discussed so many things about the importance of the meta-heuristic algorithms and all. So as we all know that why these meta-heuristic algorithms are more popular nowadays and why it is being used in almost all the fields of engineering, right? Because it is, of course, the concept is very simple and it is easy to implement. So at the same time, the most important characteristics of these algorithms are is basically these algorithms do not require any gradient or derivative information. So these are derivative free best methods. So we'll see, I mean, how these derivative free best methods are helpful in learning the features or in solving some image processing task and all. And of course, it also bypasses the local optima and it gives more chances to reach at the global optima. And there are some classifications of meta-heuristic algorithms, right? I'll not go into the details of it because some other experts might have been discussed all these things, right? So these meta-heuristic algorithms is broadly classified into various types like evolutionary algorithms, physics-based algorithms, swarm-based algorithms, human-based algorithms based on the nature of the meta-heuristic algorithms. But most importantly, I'll be focusing on these evolutionary-based algorithms in this particular lecture. Maybe sometimes some of the models like PSO, which is a swarm-based algorithm as well. So there are, if you just broadly classify the algorithms, meta-heuristic algorithms, it is of two types. One is individual-based optimization or meta-heuristic algorithms, and one is population-based. And you know that everyone is talking about population-based optimization algorithms, and also you all know the importance of the population-based algorithms compared to the individual-based, like simulated annealing. So where you have to start from a single solution and ultimately have to reach at the global solution by updating the single solution at every iteration, which takes a lot of time as well, and sometimes it doesn't guarantee to give you the global optima. So at the same time, if you're working on population-based algorithms, so population-based algorithms will give us more chance to reach at the global minima at a very less number of steps. So this is basically, you can see, right, this is the global minima, right? So how to reach at the global minima. So whether the individual-based optimization or stochastic optimization technique is more helpful or population-based. So population-based algorithms are nowadays more popular, right? So there are again two concepts like exploration and exploitation. The population-based algorithms gives better exploration and exploitation like that. So these are like the overviews, right, which you have already, right? Maybe you have studied by some of the experts and all. So my focus is like something different in this particular lecture, that how these algorithms are currently being adopted in image processing task, right? So I don't know whether right, all of you are acquainted with this image processing term, and whether you've studied image processing, whether working on this field or not. So that's why I've kept a few slides intentionally, that what do you mean by an image, and when I say image processing, what does it mean, and what are the possible tasks that are involved in image processing, right? So when I say a digital image, right, an image is nothing but a two-dimensional signal or a two-dimensional function, and mathematically can be denoted as f of xy, and like a single-dimensional function f of x, which is only depend on only one variable. But here there are two variables, basically x and y, and these variables are known as spatial coordinates here. And this f is particularly known as amplitude, and we call it as the intensity or color values or gray levels of an image. And initially, when we capture the image, so from an analog scene, so these values like x, y, and these amplitude values are continuous in nature. But with the help of a few techniques, those who are from signal processing background, they better know what is sampling and what is quantization. And the sampling and quantization both are the process which are required to convert these x and y values as well as the amplitude values from the continuous value to the discrete values. And ultimately, what we're getting is a matrix, or when we're storing this image with the help of a computer, it is nothing but a two-dimensional matrix or two-dimensional array of integer values. And sometimes, if you want, you can also normalize the value from 0 to 1. But usually it contains, if you're considering grayscale image, so it contains, I mean, the amplitude value starts from 0 and ends up with 255 if you are considering an 8-bit image, right? So I mean, if you just look at, this is an image, and where the x direction is in this way and the y direction is just horizontally right side, and the origin starts from here. And if I just choose the first position here, which is 0 0, and when I say, if you want to store this particular image with the help of a computer, then you will just see that this image is nothing but a two-dimensional matrix, a two-dimensional array of some values, mostly in integers, right? And where this f of 0 0 says the intensity values or the color values at position 0 0, and similarly the other values are nothing but like f of 0 1, f of 0 minus 1, nothing but the amplitude values or the color values or the gray level values at those positions 0 1 and this one. So this is all about, I mean, the background of what do you mean by a digital image, and what are the process involved in converting a continuous image into a digital image. And now we will see what are the key stages that are involved in image processing, and in which stage the meta-heuristic optimization algorithms have been applied successfully. So if you look at the stages here, the stages I mean, it all starts from the image acquisition, right? I mean, how this image is being captured, right? But the major stages, if you look at it, starts from image enhancement. So image enhancement is one of the key stages in digital image processing block. And when I say image enhancement, here's also an example I've given, right? You can see this, the input image here is nothing but a low contrast image, which is visually not better because most of the informations are not clear. And after applying some sort of image enhancement technique, what I'm getting is the image which is given the right hand side. If you can just easily compare that which image is looking better. So visually, of course, the enhanced image is better because most of the informations are visible clearly in the enhanced image. So when I say image enhancement, so goal here is to enhance the quality of the image. So you can focus on enhancing the contrast of the image. Sorry. And the next stage here is, let's say, image restoration. I mean, these are like different problem statements, you can say. And the whole stages in image processing, or the whole task of the digital image processing, can be divided into two parts. One is lower level image processing task, and one is a high level image processing task. So the lower level image processing tasks basically include this image enhancement, image restoration, and this morphological processing. And the segmentation, representation, and description and object recognition are nothing but the part of high level image processing task, and sometimes known as computer vision task as well. So we'll see the applications of the meta-heuristic optimization algorithms in both lower level image processing task as well as high level image processing task. So yes, we were discussing about image enhancement. We'll also see the applications of meta-heuristic algorithms in image enhancement, how it is helpful. And then when I say image restoration, let's say you are dealing with an image which is corrupted by some sort of unwanted informations like noise, or maybe there are some images which are blurred. So can you restore the image? So that is what is image restoration, right? And from the blurred image, you have to get deblur image. From the noisy image, you have to get a denoise image. That means you have to remove the noise. So there are a couple of algorithms which are available in the literature through which you can remove the noise and all, and we'll see it. Similarly, morphological processing is basically focused on binary images, right? So which is not of our interest in this lecture. And coming to the image segmentation, when I say image segmentation, I'll show you the applications as well later on. So when I say segmentation, that means image segmentation means where we want to segment the whole image into different objects, maybe sometimes the foreground objects and background objects and like that. And let's say, for example, there is a medical image, or let's say a brain MRI image is given to you, and your task is to segment that image into some certain objects. Basically, you need to highlight the tumor, the location of the tumors and the area of the tumors, let's say. And that is all about the segmentation, where you have to highlight the regions where tumor regions are there in the image. And we'll see how these image segmentation problems can be solved, and how the meta-heuristic algorithms can be applied to it. Another most important stages in high-level image processing task is image representation and descriptions. You might have heard about the term features, right? So the most important term here is feature. So how to analyze the features, how to extract the features from the images, because we don't want to directly work on the images. If you are dealing with machine learning based system, in the machine learning based system, you need to have set of features which will be passed to certain classifiers. Let's say you are solving a classification problem using probably neural network on support vector machine and all, and you cannot directly process these images into those architectures, right? So if you want to directly pass, so there will be high complexity and all. So what we can do is we need to have some representations or representatives of this image. And those representatives are nothing but known as attributes and features. How to extract those features? So there are a couple of standard approaches that are available through which you can extract the features, store the features in a feature vector. That is all about this feature representation and all. And then you have to process those features with the help of some sort of classifiers, right? Machine learning classifiers and all. So can we use the meta-heuristic algorithms to learn or to extract those features? We'll see, right? Which is very interesting. And there are also a couple of applications which we'll discuss later on. So if I want to solve this image processing task, So there are two types of approaches through which I can solve the image processing task. One is a traditional approach or conventional approach, and one is a learning-based approach. So the meta-heuristic algorithms is mostly adapted in learning-based approaches, but you will also find its applications in some of the traditional approaches. So that means traditional approaches means we are not using any learning concept, whether it is supervised, whether it is unsupervised. We're not using any learning concept to solve the image processing task. We'll see. And in learning-based approaches, we are interested in solving the image processing task with the help of some sort of machine learning and deep learning algorithms. And here are the image processing tasks which I've chosen for this lecture, right? These are nothing but image enhancement, image segmentation. There's one more application which I've chosen, very interesting applications. Is hyperspectral band selection. So hyperspectral image processing is very, very important nowadays to analyze some sort of data and all. And we'll discuss, right, how these meta-heuristic algorithms are currently being applied to hyperspectral image processing, basically for hyperspectral band selection, which is a kind of subset selection problem, which can be easily solved using meta-heuristic approaches. And at the same time, feature selection and feature learning. So you have extracted, let's say, in case of feature selection, what I want to say here is that you have extracted some sort of features from the images and stored in a feature vector without knowing whether all the features you have extracted using some sort of techniques available in the literatures, all features are important or not for us. How do you know whether all features are important or not? If they're not important for us, or if they are irrelevant or redundant for us, so we should not consider those features, because if you're considering those features, or if you're processing those features with the help of a machine learning classifier, so of course you may get some poor performance. And coming to the feature learning, so nowadays, instead of feature extraction, people are very much concerned about learning the features, and the deep learning algorithms are very, very popular in learning the features, right? So we'll see, those features are known as non-handcrafted or non-hand engineered features, and we'll see how to apply this this meta-heuristic optimization techniques to learn the features. Let us start with the first application, which is image enhancement. So image enhancement is, we have just now discussed, right? Why image enhancement is necessary, because whenever you are solving, let's say, high level image processing task, and you are dealing with some sort of images which are having low contrast and which needs to be enhanced, right? Because most of the informations are not visible properly. So if the image is of poor contrast, so then how would you extract the features from the images? So definitely you'll not get good performance with using even the best approach. So what we need to do is we need to first apply the image enhancement technique over those images which are not good visually, and then we will process those image enhanced or enhanced image for further feature extraction or for further processing, whatever, right? Usually, for image enhancement, some transformation functions are applied. And those transformation functions are either applied over a local region or point-to-point basis, or over the global image, that means the whole image. So these transformation functions could be a logarithmic function, could be a power law function, could be any type of function. But the kind of transformation function which has been extensively used for image contrast enhancement is given in this equation. So if you just look at this equation, this equation contains this E of ij is nothing but the pixel, ijth pixel of the enhanced image, and the corresponding pixel in the original image is O of ij. So O of ij is nothing but the corresponding pixel in the original image, I mean the ijth pixel in the original image, where E of ij is the corresponding pixel in the enhanced image. And the rest others are nothing but the new terms that has been introduced and to design this transformation function. If you apply this transformation function, which works both locally and globally over the image, locally means it is applied on some windows. That means it is taking the informations from a local neighborhood to change the particular pixel in the enhanced image. And if you look at this equation carefully, so it contains few more terms like m of ij, m of g, and the sigma of g. These are nothing but mean values. When I say m of l, it is the local mean, and this m of g is the global mean of the image. And similarly, the sigma is nothing but the standard deviation of that particular local region. And rest of the terms, if you look at this a, b, c, and k are the four parameters which controls this image contrast here. So basically what we want to do here, so we want to stretch the image, stretch the gray levels of the image from one range to another range so that the image will visually appear better. And if you look at, what we have found out just now, that this equation, this transformation equation contains four parameters which takes different values, and these values are generally set manually. So that means in general set manually, and it is very difficult to get a good combinations of these values of a, b, c, and k. So that is where we need optimization techniques to get the optimal values of a, b, c, and k, and ultimately the kind of result which you will get is visually better than the manual approach. And that is why this a, b, c, k needs to be optimized. And this is a transformation function which are applied. The kind of fitness function which has been applied along with this transformation function for solving, because this has been considered as an optimization problem, so we can use any of the optimization techniques here. And the fitness functions here, if you look at, I've just taken this fitness function from this paper, which is a paper published in 2017, right? And this fitness function, if you look at here, contains three terms. It's a combination of three terms: entropy, standard deviation, as well as age informations. So why they've actually taken, initially if you go through the literature, you will find that people have only taken entropy values in the fitness function, and later they have combined some other informations, right? Entropy basically tells us the information contained in the image. And if you look at the age information, why there is a need of age information here, why they're including this age information into the fitness function, right? Because age information tells us, so when you are enhancing the quality of the image or the contrast of the image, so it will visually looks better. So that means the age informations also will be very prominent compared to the original image. So that is why they are considering the age informations, because what they are expecting that yes, the age informations will be more in the enhanced image after applying the transformation function. So that is why they are considering age informations along with the entropy. And using this using this fitness function and this transformation function, they have applied over some satellite images, in this paper. So I'll show you the results as well. Yes. So if you look at this figure, the results, basically the first figure is nothing but the original image, where we have chosen only two parts, highlighted in red color and green color, and these are nothing but the zoomed version of these two parts of this particular image. And here you can see this image is basically, it's low contrast in nature, because the water lines and there are so many objects which are not clearly visible. And if you look at the image which is given in D, which is, most of the regions are prominent, the water lines and all, so many things are prominent here, right? And this is the result of the proposed technique, which is nothing but modified differential evaluation. Basically, they have used differential evaluation to optimize this transformation function with the help of this fitness function. And these are the results. And if you if you look at the results that has been provided in figure B and figure C, these are nothing but the results obtained by differential evaluation and Kuko search optimization. Probably you might have heard about, there are a lot of optimization algorithms available in the literature, right? So mostly they have taken differential evaluation, and they tried to update or modify the differential evaluation by introducing some sort of mutation operators into it to increase the diversity of the algorithms and all. And what they are claiming that, if you just look at this outputs, right? If you look at this output, so this image is much more visually better compared to the original image. Even the images that has been obtained using the standard differential evaluation algorithm and the Kuko search algorithm. You can just see the zoomed part also. The information is pretty clear in the or using the modified differential evaluation algorithm. Okay. So here is another example taken from another paper, which has been applied to grayscale images. So previous one was like color image. So there's a grayscale image contrast enhancement applied over some images using PSO, particle sum optimization. And here are the results. You can see the original image is given in figure number A, and then the B, C, D, E are like the results of linear contrast stretching. The contrast stretching is some of the traditional approach through which we enhance the contrast of the image, which is not sufficient to enhance the contrast of the image. You can see also here that most of the informations are still not visible properly. And then the next one is the output of the histogram equalization, which is one of the most popular approach or global approach, which basically enhances the global appearance of an image. And then you can see the output of genetic algorithms in figure number D, but the output of PSO is given in figure number E. And you can see the informations which are not clearly visible on the darker in the original image are still darker in the outputs of by the different techniques like genetic algorithms and histogram manipulation, but it is now properly visible in case of particle sum optimization, right? So I mean, this is how, and the kind of fitness functions they've adopted also the same function, the same transformation function, which contains 4 different parameters which needs to be optimized, and those 4 parameters are optimized with the help of PSO. And the kind of fitness functions they have adopted is this one, which contains is the combinations of this, basically is nothing but a combinations of 3 things. One is entropy, which is h of IE, entropy of the enhanced image, and the sum of intensities, basically the sum of edge intensities, because what they're expecting that the number of edge informations will be more, right, compared to the original image. So that's why they're also including the sum of edge intensities as well as the number of edges. That means the number of edge pixels which will be more in the enhanced image compared to the original image. And these three terms has been multiplied and considered as a fitness function in this particular work. And what they've got is this result, is improved or enhanced result compared to the other methods. Coming to another applications of image processing, which is image segmentation. So image segmentation, if you see, if you go through the literature, you will find that multi-level or thresholding is one of the approach, simple approach, which has been applied extensively, right, in early days to solve image segmentation problems. And also there is an unsupervised learning algorithm known as k-means clustering, which you might have heard about, is also very popular for image segmentation, right? So we'll see how, I mean, this meta-heuristic techniques has been combined with these techniques, right, to give the better performance in case of image segmentation. And for multi-level thresholding, if you just look at, so I've just taken other idea from this paper, right, just published in Pattern Recognition Letter 2015. So what they basically did is they, in multi-level thresholding, your goal is to um, decide multiple thresholds, right, and ultimately divides the image into multiple objects, right? So, and these are some of the steps which they have followed, right, in their paper to get the segmented output. And initially they convert that original image into some other color space because it gives more informations. And then they applied this differential evolution, again the differential evolution technique, right, optimization technique, to get the threshold values, which I have already told, that because getting the threshold values itself is a difficult task, because it's purely manual procedure. Through manual procedure, we need to decide the threshold value, and sometimes if there are multiple objects, it is very, very difficult to decide a threshold value for each of the objects, right? So it is better to have some automated approach through which you can get those threshold values by looking at something, right? And this is what is the optimization technique is. So what they've applied is differential evaluation along with the minimum cross entropy as a fitness function, right? And to get the threshold values, and they've solved the problem, multi-level thresholding approach. I'm just giving the ideas that how these meta-heuristic techniques have been applied. So if you want to work on it, so you can just go through these papers in detail, and you'll get to know about how actually this problem can be solved easily using meta-heuristic techniques, and what was the issues with the traditional approach. As I said, that because it was manual, and if you want to make it automatic, so then we need some optimization techniques. So mostly differential evolution, genetic algorithms, and there are a couple of other algorithms can also be explored in this field. So coming to another work, which is uh, how to combine the meta-heuristic optimization techniques like PSO and maybe some other techniques as well, right? Along with the k-means clustering to avoid some sort of issues that k-means clustering always face. So K-means clustering is a very popular clustering algorithm, which basically clusters, right, the samples of the similar categories. So here also we want, so segmentation can be considered as a clustering problem where you need to cluster the similar type of things, right? So basically, if they belongs to a single object, so then there will be a one cluster, or probably if they belongs to a different object, so it will be another cluster like that. So that's why K-means algorithm is very popular in solving image segmentation problem. So then where do we, I mean, why do we need optimization algorithm here? Because k-means clustering can also be converted into an optimization problem. It's of course, it's an optimization problem. So it's an optimization problem. So what kind of optimization problem and how the fitness function will look like? So this is what is the fitness function which will look like. So if you look at and the equation, if you look at this equation, where m is the total number of samples, and xi is the the sample, and mu of ci is nothing but where if the sample belongs to a particular cluster, then the distance between that particular sample to its corresponding cluster. So you have to find out the distance for each of those samples to their corresponding clusters, and if the distance is minimum, so you have to find out such particular centroids, you can say, or the cluster centers for which the distance is minimum, right? So then your job is over. And this k-means clustering always, there are two issues in k-means clustering. So you have to first decide the k value initially. At the same time, you have to also decide the k number of clusters as cluster centers, right? Which we usually choose randomly. But because of this randomness, in choosing the cluster centers, it gives us different results. And sometimes even it falls to the local optima, where you are not getting the global minimum value, rather you are getting some local minimum values, and we miss always the global optima, right? So then this is where actually when we talk about it is missing something, it is falling in the local optima, and it is missing the global optimum value. So definitely we'll think about some sort of optimization algorithms, right? And of course derivative free, because it has a lot of advantages, right? So then people have thought about applying this particle sum optimization algorithm along with this k-means clustering approach. And this is I mean, I'll show you. And you can just go through this paper, and you can just check the results whatever they've obtained, right? And they have also compared the results with the traditional k-means clustering algorithm. At the same time, the results obtained by combining this particle sum optimization with this k-means clustering algorithm, right? So idea is very simple here. This is the fitness function. The solution vector will look very simple, that you have to choose the number of the cluster centers, right? Let's say the k value you have chosen as 5, so you have to choose the cluster, I mean, you have to choose k number of samples from the data set, and which will behave as the cluster centers. Initially those will be considered as a population for us, or if those are like each particle for us, and then it will update those particles with the help of this particle sum optimization. And probably they have used dynamic particle sum optimization. Probably you know that in particle sum optimization there are parameters like c1, c2, there's a inertia, weight, and all. So they have just modified they've just given some formulas to find out those control parameters, basically c1, c2, and all. And I mean, mainly they've made it adaptive, you can say, right? They have just proposed a formula to get the adaptive values of the c1 and c2 in an adaptive manner. That's it. And finally, they have claimed that they are also getting better results compared to the standard PSO, right? When the standard PSO is combined with k-means clustering, and when this dynamic PSO is combined with k-means clustering, they are getting better results compared to the standard PSO. Okay. Okay. So coming to another kind of application, and there are a lot of papers that have been published, right? And in the past decade, you can say in the past 2 decades, right, where you will find the applications of meta-heuristic algorithms in image segmentation. You can just go through it and you can find it out. Coming to another kind of application, which is hyperspectral band selection. So I don't know how many of you have heard about the term hyperspectral imaging, right? Which is a very, very important uh, domain, right? Because there are few things which you cannot capture through the normal cameras, and you cannot analyze. You cannot get the spectral informations, right? So the spectral informations are very, very important to analyze some sort of information. Like if you want to analyze the soil, if you want to analyze, or if you want to develop a particular city in a particular area. So if you want to know that where a city can be built, and the water area, the lot of things, right? If you want to analyze, so by capturing just a photo from a drone, you cannot get all the ideas, right? Because there is no spectral information. So whatever you're getting is simply a color image, right? From those images, you will not get all those informations. So that is where actually this hyperspectral imaging is important, and this hyperspectral imaging keeps us the spectral information along with the spatial informations, which are helpful in analyzing the data and ultimately getting more informations, right? So but uh, if you just download this data, and if you want to process this hyperspectral image with the help of a computer, the task is a bit complex compared to processing the natural images, right? Natural RGB or natural color images, because the natural images, RGB images, contains only 3 channels. But if you process the hyperspectral images, so it will be having even more than 100, sometimes more than 200 number of channels. So that means analyzing hyperspectral images is a bit complex compared to the traditional image. So that means an image can have a particular hyperspectral image can have more than 100 or more than sometimes even 200 channels, so we can call it as bands. But as you all know that not all bands are important, right? Sometimes there are some redundancies in some of the bands or spectral bands. So can we identify those bands? Because do we always need all those bands, or can we remove or ignore some bands which are not important for us, not for our task? So this has led to an problem statement known as hyperspectral band selection. I hope you got the idea that what do you mean by this band selection here, and why do we need this band selection here, and why do we want to select the band? Because there are multiple bands you have to work on, and if you can reduce the number of bands, of course, your further processing will be easier, right, with the help of some sort of algorithms. And if you find that yes, all bands are important, that is fine, but not all the time all bands are important. So we need to identify those irrelevant or redundant bands. So the kind of problem, right, the kind of optimization, it can be considered as an optimization problem, which is, and but this kind of optimization problem is a binary optimization problem. Why I'm saying it's a binary optimization problem, because here the solution vector will be like will contain, let's say, if you are considering this particular image, which is a high dice decimal, which has been taken from the high dice decimal data, which contains 191 subbands. So you will be having the solution vector contains 191 values for each of the pixels. For each of the pixels, you will be having 191 values, right? Like in color image, if you are considering each pixels, you will be having 3 values for R channel, for G channel, for B channel, for red, green, and blue channel. So similarly, for every pixel, you will be having 191 values over here, and you want to select only one among them, right? So that means what you need to do is, I mean, so similarly, you can just represent the whole image in the form of that. That means what you want to do is you want to simply sorry, so you want to simply select those bands which are important for us. So then why I'm saying it's a binary problem, because the solution vector will look very simple, will have the values only 1 and zeros, and the dimension of the solution vector will be 191. And the solution vector will contain only values 1 and 0, where 0 means that the band is not selected, 1 means the band is selected. And again, you will apply some sort of the population based approach. So then you will modify, or you will update the weights, or you will update the positions of the PSO if you're considering PSO, and you will update the solution, and ultimately end up with the best solution, right? By looking at some sort of fitness function over here. The fitness function can be, again, maybe let's say this is a classification problem. So you can consider any learning based approach here. Let's say you are considering k nearest neighbor, or probably some sort of other algorithms. So you can just look at the accuracy. So at the same time, you can also look at some other things, or you can include some other things into the fitness functions, which are very important in this case, like some class separability could be one of the uh, important parameters which can be considered along with the accuracy together to build a combined fitness function, right? So just now we've discussed that this band selection problem is similar to feature selection problem, which also I will discuss later on, and that is why it is a binary problem. So to solve this problem, we need the binary versions of the meta heuristic algorithm. So and every algorithm has its own binary versions. Right? We all know that because genetic algorithm is by nature, it's binary in nature because the solutions itself are given in 1 0 and not in that format. And PSO is by default it handles the real values, so you have to go through or you have to use the binary versions of the PSO to solve this problem. Right? There are different types of approaches available in the literature, right? I mean, different approaches have been proposed uh, in the literature to design the binary versions or binary variants of the PSO algorithm. And similarly, for differential evolution and some other algorithms as well. Here is one results which I've taken from one paper in from the IEEE Journal of Applied Earth Observations and Remote Sensing. On the same data, I mean, this is a classification task basically where you have to classify each of these pixels over here, right? After selecting the bands, right? The results of which you can see the results obtained by their proposed approach, right? So, I mean, using PSO, basically they have used two PSOs, right? Not one PSO, two PSO. That's why it is written two PSO. And if they're using one PSO and what the kind of accuracy they're achieving is 95, and if they're using two PSO, then they're getting an enhanced performance in terms of accuracy, which is 97.01. So now if you just look at the visual outputs or the visualization results provided in six different figures, right? Soft figures like A, B, C, D, E, F. Right? So these are like the results obtained by different approaches. And the last one is the result obtained by the proposed approach while considering all the bends. So if you're considering all the bends, so there are some misclassifications. You can see there are some regions over here and which where you are getting some, I mean, the number of classes is basically 6 here. There is, and the class names are like road, grass, shadow, trails, trees, and roof, right? You can just, and the colors are also given like this. The roof is given or highlighted using orange color. So you can see the roofs are correctly classified, right? By using the proposed approach, I mean, which is the 2 PSO algorithm. This is the loops are correctly classified, but here are some misclassifications, right? I mean, that means the misclassifications means yellow color. That means the loops are uh, uh, classified. The roof basically these parts are misclassified to some other classes. That's why some yellow color pixels you will find over here, right? So that means while considering all the bands, you are getting some misclassification. That means the accuracy is reduced from 97 to 93. So that means band selection is a very important problem statement in hyperspectral imaging, because while considering all the bands, we are getting reduced performance, right? But by selecting the number of bands from the 191 bands, so what we are getting is an improved performance. The similar type of problems can also be solved using PCA. I mean, here the results are given, the results of the PCA is also given in this figure, sub figure E, you can see, right? So PCA is principal component analysis, which basically reduce the dimension, let's say from 191, but the approach is something very different. And the selection approach is something very different, right? Because PCA basically linearly transform, right, a high dimensional data to a lower dimensional data, where you are not retaining the original bands, rather you are combining the bands and then ultimately reduce the dimension from 191 to 6, because they have chosen here 6 PCs. That means 6 principal components, right? And to reduce the dimension from 191 to 6. And but the selection is something very different, where you are retaining the original bands. You are simply not or ignoring the bands which are not important for us. So that is what is the basic difference between the transformation, the band transformation, and the band selection. So coming to another type of application, which is feature selection, we'll also see how we can extract features with the help of how we can extract this with the help of meta-heuristic approaches. But before that, I would like to show you that how these feature selection problems can also be solved using meta-heuristic approaches. So when I say feature selection, that means, let's say I have used some traditional approaches or feature extraction approaches, which is available in the literature. Maybe there are images given to you, and from image we can extract different types of features. It can be color feature, it can be texture based features, it can be image transform based features. So it can be shape based feature, geometry features. So it can be of any type. And unless until you are an expertise in the domain of feature engineering, you cannot directly decide that what type of feature you should select or what type of features you should extract from an image. So what we generally do is we can simply uh, extract the features using multiple approaches and combine them together, right, to get the or to enhance the discriminant capability of the features vector or the feature set, you can say. Let's say I have extracted the features having dimension d. I mean d. That means d number of features from using any algorithms or maybe combinations of the some of the algorithms, and I want to select the d dash number of features from a set of d number of features I have selected. So that means, in summary, I can say that I have extracted small d number of features, and I want to remove the irrelevant or the redundant features from the set. It can be considered as a optimization problem, where the solution vector in that optimization problem will look like this. The solution vector will be having the dimension same as the feature dimension d. However, the values that the solution vector will take the values either 0 or 1, because it is again a binary problem. It is again a binary task. So where you want to solve or where we want to select the features, right? Either select the features or you will remove the features, right? So that means 0 means you are not selecting the feature, 1 means you are selecting the features. This is the representation of a single solution, and you can just form a population, and you can apply any algorithms. Any algorithms means variant, I mean the binary variant of any algorithms, right? Genetic algorithms can be directly applied. The binary variants of PSO, differential evolution, can be applied, right, to get the final solution. And in the final solution, let's say you are getting that there are d dash number of ones, and there are or rest and the rest of the values are 0. That means you have to only choose those features from the data set, and yet again you have to process those selected features, right, with the help of some sort of classifiers. So while considering this feature selection problem, or while solving this feature selection problem using meta-heuristic optimization algorithms, so we require three components. Basically, we need a learning algorithms, and we need a search procedure, and at the same time we always need like every problem, every optimization problem, we need an optimize or fitness function, right? And this type of feature selection approaches are popularly known as rapport-based feature selection approaches, where we always need a learning algorithms, right? So this is how actually we can represent a solution vector, you can say. And the fitness functions in this case you can consider as like, classification accuracy and maybe the classification error, right? You can like that. I mean the misclassifications like that, rate, misclassification rate and all. And if you are solving some other problems, right? So you can also similarly consider the fitness function which is best suitable for that problem statement. So you will find also a lot of details of these approaches, right? Also we have done some works, right? And maybe 4 or 5 years back, so we did some sort of work in selecting, applying some sort of algorithms or designing some binary variants of algorithms like say, sine cosine algorithms or some other algorithms, right? The binary variants we have also compared with the binary variants of differential evolution, binary variants of PSO along with that, to solve this feature selection problem. And you'll get the details of this is a very popular paper. Actually, you will just find, because the paper has been cited more than 6,000 times, so you will just get some more information if you want to work on this feature selection problem and all. And there is another problem which is very close to this problem statement, known as image feature selection. I mean simultaneous image feature selection and parameter optimization. What does it mean? So that means, let's say you want to select the features as well as you want to update the parameters, or you have to find out the optimal values of the parameters which are involved in some of the learning algorithms. So then how to solve this problem? So this problem, now the solution vector or the solution representation will look very different from the previous one. It will contain some parameters as well as the feature values. But some values are real values because the parameter takes the real values. And and we are solving also a feature selection problem which will take the values either 0 or 1. So the solution vector will look very different from the solution vector which we have chosen earlier. For this parameter optimization, you will find lot of papers, right? I mean, to optimize the parameters of neural network, to optimize the parameters of support vector machines. So probably a lot of papers you will find. So for simultaneous feature selection and parameter optimization, you'll find less number of papers, of course, because it is a bit complex problem compared to the either feature selection or parameter optimization problem. And the kind of fitness functions, so this is actually, I mean, we did this work even 3-4 years back, right? So one of the in one of our papers, so the kind of fitness functions which we have chosen, because what it seems that here there are two goals, right? So one is like you want to improve the performance of the model. At the same time, you want to reduce the number of features. So it is a kind of multi-objective optimization problem, right? But what we made it, we just convert that multi-objective function into a single objective by considering the classification error, right? Which you want to, I mean, which needs to be minimized. So at the same time, the number of features needs to be minimized, right? So now, so both are like minimization problems right now, and then both has been combined together along with two control parameters, right? It is like alpha into 1 minus alpha, right? So I mean, it all depends on the kind of importance which you want to give to the classification error rate or to the subset of the features which you want to select, right? So this is the fitness function which we have used to solve the simultaneous feature selection as well as parameter optimization problem, and we have got some interesting results as well, right? Sorry. So coming to the most interesting problem statement, right? You can say in the field of image processing is like feature learning, right? So where our goal is to learn the features directly from the image, not using some sort of traditional approaches. So in the previous case, whatever I've discussed, so where we have extracted the features and then we were selecting the features with the help of meta-heuristic approaches. But this is something very different. So this is like how to learn the features directly from the data with the help of the meta-heuristic approaches, right? So there are approaches you will find which are very popular nowadays, and this kind of techniques are known as non-handcrafted feature extraction approaches. And there are convolutional neural network you might have heard about, which is a deep learning based approach. And autoencoder is again a kind of deep learning architecture which are very popular for extraction of the non-handcrafted features. But as we all know that these methods are again gradient or descent based or derivative based, and sometimes also suffers from some overfitting issues because they always demand a huge amount of data for effective training. So now the question is, can we design a non-handcrafted feature extraction approach, right, which is free from derivative and in the presence of limited samples, because the CNN and all always demands huge amount of data. So can we have some sort of algorithms which is free from derivative as well as it will extract important features in the presence of limited samples. So this idea, we developed one algorithm or known as evolutionary convolutional network. So this is not convolutional neural network where we have used neural network to solve the problem, not like that. So just we have used the concept of convolution, right? And design, and this convolution is very good at extracting the features, right? As we all know, and because and the filters are very important, and those filters are always trained using the loss functions, right? In the traditional convolutional neural network, where you will also find some sort of neural network layers at the end, and ultimately you will focus on the only one function, that is the loss function, and based on that loss function and the backpropagation learning algorithm, you will update the weights, and sometimes also you have to face the vanishing gradient issues or maybe some other issues and through which you have to solve the problem. But this method is something very different, which we have designed in the year 2021, and we have applied it to some sort of medical data set. I'll also discuss about it. We've applied this on the retinal fundus images to detect glaucoma. Glaucoma is a kind of eye disease. I'll also give you the idea behind the glaucoma, right? I mean, what it is giving and the kind of results which we have obtained, and what was the goal actually. The goal was very simple: to design an architecture which is free from this derivative-based optimizations, like in the traditional approaches, and but the goal is also to use the benefit of the convolution layers, right, along with some sort of activation functions like ReLU and all. So this particular part, if you look at here, is nothing but is a convolutional network. It's not convolutional neural network. It's just a convolutional network where you will find multiple layers of convolutions and ReLUs and all. And finally, what we're getting is some sort of features, but we don't know whether these features are important for us or not, or whether these features are optimized features or not. So then what you can do is we have to update the features, right, by looking at something. We're not looking at the output. We're not looking at the output here, right? So we are just looking at the quality of the features. That means you can say that it is unsupervised in nature, so it is not supervised. We're not looking at the output at all, right? So the kind of fitness function, the kind of function which we are looking at here is that is maximization of the interclass distance and the minimization of the interclass variance, right? This is the actually function, right? And that the particularly this network is trained with the help of this criteria, and this is considered as the fitness function over here. One is a minimization problem and one is a maximization problem. So then you can just think about that, what kind of optimization problem can be applied over here. So we have applied real coded genetic algorithm because the kind of the solution vector here contains the values or the real values, right? Basically, and the filter values and the other values are here the real values. So that's why we're adopting real coded genetic algorithm to solve this problem. Also, we have compared with PSO and differential evaluation as well. And the idea was very simple, that as it contains certain parameters here, right, in the convolutional layers and other layers. So how to get the good features, right? I mean, how to get some prominent features from the input images by looking at, or by using, of course, some sort of optimization technique, and by looking at some sort of the objective values. The objective value is pretty clear here. And this is the idea, common idea, which you always apply, right? The maximize the interclass distance and minimizing the intraclass variance. So this also tries to discriminate the features of the two classes well, and so that we can have get discriminative features, right? Basically, it helps in getting the discriminative features through which we can easily discriminate the samples of the different classes. And then after getting the final features, right, using this procedure, right, using this iterative approach, and the final feature set is can be passed to any classifier to solve the problem, right, classification problem. So I mean, I'll just give you some brief idea beyond this problem statement which we have solved using this evolutionary convolutional network. So the idea was like I mean, analyze the retinal fundus images, which are popularly used for detecting ophthalmic disease. And one of the diseases which we have considered is glaucoma, which is a very common disease nowadays, right? And which basically damages the optic nerve, right? I'll also show you the kind of the retinal fundus images which are used to, and how these ophthalmologists are being detected. I mean, how they are detecting this glaucoma disease manually. So this glaucoma, here are some of the statistics I've just put, right? The statistics is that around 64.3 million individuals aged 40 to 80 and finally at the advanced stage, they can't able to see. I mean, it will be pure vision loss. So then what is important here is to identify those patients at an early stage, because this kind of disease is purely irreversible, right? And if you can detect it at a very early stage, probably we can save many lives, right? Okay, so that is why it is very important to detect this kind of disease at an early stage. And at an early stage, because in the early stages the patients are unaware about their conditions, their eye conditions, because there is no such symptoms, or it is like asymptotic at the early stages. So only the regular checkups, right, or the regular analysis of these fundus images may help us in preventing glaucoma. And there there are some reasons behind the glaucoma. I mean, the possibilities of the glaucoma patients, like whether it is genetic, whether it is whether the patient has some history or the family history and all like that, right? So based on that, doctors used to recommend that we should go for a fundus image analysis test, and based on that image, the the ophthalmologist used to identify whether the person is having glaucoma or not. But it's a pure manual process, and I'll just show you that how manual it is and how difficult sometimes it is, right? So here is an example of this fundus image you can see, and of a normal eye. That means of normal patient, I mean, not having glaucoma. And here is the fundus image at the right side. You can see the fundus image of a patient who is suffering from glaucoma. So, as I said already, that the glaucoma basically damages the optic nerve, and in the image, the optic nerve looks like an optic disc here, a disc, right? So there are actually two concentric circles here. One is like optic disc, the outer circle, and the optic cup is the inner circle. So what they usually do, that they manually used to find out the diameter of these two, and then find out the ratio between these two, the two diameters. Like, it is like known as cop to disc ratio, right? And if the ratio value is more than 0.5, so then that means the patient is in early stage. Or if it is greater than and based on the CDR value, basically they used to decide that whether the person is suffering from glaucoma or not. You can see for the glaucoma patient, the ratio is more. I mean, the CDR value is more. So this is a pure manual approach, and sometimes even it is very, very much difficult to identify or to detect the disc part, as well as the core part. So and then you will find some difficulties to identify or to get these CDR values and all. And sometimes even at the early stage, it is difficult to get a proper appropriate CDR value. So that is why an automated approach is very, very important here, which will help us in analyzing those images and ultimately help the ophthalmologist in accurately detecting and whether the person is having glaucoma or not. And to solve this problem, actually, so we have applied this approach, this evolutionary convolutional network, because convolution operations are very good at extracting the features using different set of filters, and and then to just extract those, I mean, the discriminant features from the input retinal fundus images. We have applied this technique, and the results are here given in this table, where this real coded genetic algorithms has been adopted by us. And the classifiers, as I told, after extracting the learning the good features, the prominent features, with the help of the optimization technique, so we can apply it to any classifier. So we have chosen 5 classifiers, like K nearest neighbor support vector machine. There is something called the extreme learning machine. There's a kernel extreme learning machine, which is a kind of single layer fit for all neural network, and it's basically comes under the category of randomized neural network. And there's a backpropagation neural network as well. So if you just look at the kind of the performance, or if you just look at the kind of performance which I've got is higher in case of RCGA compared to differential evolution and PSO, right? And there are several other results also we have reported in our paper. If you want, you can go through that, right? And here is just the comparison of our approach known as ECNet with the other standard machine learning approaches, where the features have been identified manually, or and then use some sort of classification approaches. Also, we have compared with some convolutional neural network based approaches, right? And if you just look at the performance, and all these algorithms has been validated on the same training setup. That means all have been trained. I mean, the training testing protocol was the same for all the methods, and the kind of we have got higher performance compared to the others. And if you look at the number of parameters, as I said, the number of parameters are also less in our case, which is 0.003 million, and compared to the CNN approaches, which have also got comparable performance over here. And if you look at the number of parameters required by these CNN methods and these autoencoders and all, it is like 13.6 million, 3.5 million. And compared to that, our model requires very less number of parameters. It's lightweight in nature, and it gives also better performance in some data sets. So ECNet has a lot of advantages over the other methods which are important in learning the features. So we have just now seen some sort of advantages, like it requires a lot of pure, I mean, a lot of it requires less parameters compared to others, and it is free from derivative, right? And it can give us also high-level features like convolutional neural network with less number of samples, right? So these are some of the advantages of you can say ECNet over other techniques which are good at learning the features. So till now, what we have seen that the different kind of applications of image processing, starting from image enhancement, image segmentation, hyperspectral band selection, feature selection, and parameter optimization. At the same time, feature learning. Right, there are a couple of applications which I have seen. Now we'll see, because everyone is right now talking about convolutional neural network, right? So there are also a couple of issues that we face while dealing with convolutional neural networks. So in convolutional neural network, mostly you will find the approaches are gradient based. I mean, the learning approaches, basically the optimization approaches are gradient based, and it also gives good results. But it also at the same time it contains lot of hyperparameters. So we need the adjustment of hyperparameters. There are several hyperparameters we have in convolutional neural network. So we'll find some papers in the literature which tries basically to adjust the hyperparameters of convolutional neural network. And coming to the parameters, which are always in the form of millions, which is a bit difficult, right? We all know that. So there are less papers where you will find that the meta-heuristic approaches have been applied in CNN to update the parameters, but you will find more papers to update the hyperparameters because the numbers are less. And this is again a challenge. It's not that easy because every hyperparameter is having different range. So what I'm trying to say here is, let's say you are choosing, let's say you are having 10 hyperparameters in your convolutional neural network, and this is how actually the traditional or sequential convolutional neural network looks like, which contains some sort of layers, convolutions, very good at extraction of the features over the different layers. We have repeated it, convolution followed by pooling. The pooling is a layer which doesn't contain any parameters but helps in reducing the parameters, or else the number of parameters is going to be very high. So at the end, I mean, this convolution ReLU pooling is repeated over the times and over certain layers, and then finally you will get some of the fully connected layers. And these layers are fully connected, means every neurons in this layer is connected to every other neurons in the previous layer, and it is very similar to the layer which we have seen in traditional neural network. And ultimately there'll be one layer containing softmax. If you are solving a classification problem, then you will get some sort of probability values for each of the class, and based on the maximum probability value you will decide the class level, right? So the softmax is the activation function, so which basically gives us the probability values, and if you add them together you will get the value 1. But in case of sigmoid it is not possible, right? So that is why softmax is more popular nowadays, which are used to solve classification problem. But this is just a simple convolutional neural network approach, which is sequential and very simple. But if you just combine, if you just go through the literature of the CNN, you will find that over the time there are different types of convolutional neural network that have been developed. But the number of hyperparameters, the number of parameters are very large in this case. So how to just get the optimized value of the hyperparameters? Of course, when we say the optimized value, so then people have tried to apply some sort of meta-heuristic techniques. I've not taken, or I have not shown any papers here. But if you just go through, there are also papers like survey papers where you will find um, the usage of convolutional neural network. I mean, the usage of advanced optimization algorithms in convolutional neural network, and where it has been mostly applied. So similarly, so because the design of the convolutional neural network is some sort of manual, right, approach. It's a manual procedure. I mean, deciding the number of layers, the kernel size at every convolutional layer, the deciding the stride and all. Also, it is also a kind of because if you are choosing different number of layers, you may end up with different results. So then how to choose this? Because it seems it's a tedious job. So people have also tried to apply meta-heuristic approach in solving this type of problems. And last but not the least, the most important one and the current trend in convolutional neural network is the neural architecture search. What does it mean? So it is very important to understand what do you mean by the neural architecture search. So that means, as I said, that the CNNs that has been developed over the years are manually designed in general, and if you're having rich expertise, then only you can design it, right? And of course, there are a couple of new things that has been introduced, but how many layers, and there are a lot of other things as well. So that's why in every paper you will find that they are giving, more than 5 architectures, like a small architecture, medium architecture, large architectures, right? And how would you know that which architecture is best for solving a problem given at hand? So because this design process of the CNN is labor intensive, and because it's a trial and error process, right? So can we have, or can we automatically, or can we design some automated approach through which we can design the CNN architecture, and which is known as neural architecture search. So there are different approaches that has been proposed in the past years to develop neural architecture search methods, but evolutionary computation based methods is one among them, and has also gained a lot of attentions from the researchers in the past few years. And if you want to define this neural architecture search mathematically, it is nothing but it can be considered as an optimization problem again. And if you look at this equation here, what it says, that you want to find out a best architecture where this particular A is defines the search space, right? Here the solutions are like, every solution is nothing but an architecture here, right? So every particle will be one architecture. So then you have to finally end up with one architecture which is best for a problem statement, right? And for which we always do trial and error process to get a final or a good architecture. So instead of that, can we apply some evolutionary algorithms, right, to end up with a best architecture or optimal architecture? So I mean that means I mean this particular aim, I mean it's a minimization kind of problem. That means you want to, let's say, minimize something, right? So the fitness function, of course, here, right? So that means I want to find out that particular A which belongs to this A. That means from this source space of the neural architecture, and you want to, I mean that means you want to find out that A for which this function is minimum. And what is this function? I mean, of course, this function is nothing but you have to compute the fitness function over here. The fitness function could be anything here, maybe the classification error, or maybe some other things, right? Which is applied on the training set, because we are mainly dealing with the training data to design the architecture and all. And it can be easily considered an optimization problem, but this optimization problem is not like a very easy optimization problem which we have seen earlier in early cases, right? So it's a bit complex problem compared to, because there are multiple criteria, and maybe some criteria is conflicting with other criterion, and similarly there are some other things like there are constraints, like complex constraints, not simple constraints and all. So it is a bit complex problem compared to the other problems, but can be solved with the help of evolutionary based techniques, and which is popularly known as ENAS, evolutionary based neural network, neural architecture search. And here is just the flow chart of commonly used evolutionary based NAS algorithm. The same thing which you have seen in case of traditional optimization or metavistic optimization approach. Here also you need to initialize the population, look at the fitness, and then update the population based on some criterion. If you are using genetic algorithm, then probably genetic algorithm, we all know that there are processes like crossover, mutations, which will give us new solutions, and again we have to choose the best solutions from each of the generations or from each of the iteration, and then we have to repeat the procedure till we end up with the, or till we reach the stopping criterion, or till the algorithm is converged, right? And ultimately we'll end up with the best architecture. That is what we know. So here every individual in a population is nothing but an architecture, but we have to first encode that architecture in the form of a solution vector. If you can encode it, then you can easily solve the problem, right? So how to encode it? So there are different methods through which encoding is possible. And one of the approach is like operation encoding. I mean, it's a very simple encoding process where you can encode every fetch or every step of the convolutional neural network, right? With the help of a binary representations. Of course, I mean, if you know how to encode a directed acyclic graph, then you can can use the same procedure to represent every node here in the form of a binary representation, and where in this case every node is nothing but a single operation or maybe a combined operations like convolution, pooling, batch normalization, or maybe a sequence of operations. So you have to just represent every network with the help of a vector, which is nothing but a combination of vectors, and you can see where x naught is equal to x naught 1, or sorry, this will be x naught 2, and this will be x naught np. That means, let's say my architecture contains np number of blocks or np number of phases, right? And where every block is nothing but a binary representation. And when we're combining them together, it will just become the encoding or the solution vector for a particular architecture, because here every solution is an architecture. And then you have to apply the algorithms, right? Apply the algorithms. I mean, the meta-heuristic algorithms mostly uh, sorry, mostly the evolutionary algorithms, right? And like genetic algorithms and all. I mean, this has been applied. Maybe other algorithms can also be applied easily. So this is, I mean, I'm just giving you one example I've taken from this paper, this NSGNet, right? So you might have heard about this neural architecture search using multi-objective genetic algorithm. So maybe some of the experts might have discussed about this NSG and all. I mean, when probably the genetic algorithm and multi-objective genetic algorithms, and how these things can be also applied here to design neural architecture search algorithm. So I just want to highlight here something very interesting, right? I mean, what we can generate only using a simple, how a crossover operation in genetic algorithms helps in generating an interesting architecture, right? So I don't know how many of you have heard about the CNN architectures, which are very popular nowadays, like VGGNet, DenseNet, ResNet, or maybe many more architectures, which are very, very popular. And even we know that the architectures like AlexNet, the very, very popular architectures. People have also been awarded Nobel Prize this year, right? So who developed AlexNet as well. So how a crossover operation, right, helps in generating one architecture, right, using two other architectures, right? That is what is actually I want to showcase here to all of you. So you can see, so this is the parent one, the solution of this parent one. It is just like one block which I've chosen from the VGGNet. It's a it's a sequential one, right? One after another, one after another. And this parent two, let's say here, is a kind of architecture which is close to DenseNet block, where you will find multiple connections from one layer to another layer, right? Which are known as dense connections. And a simple crossover operation results in another architecture, which is a ResNet, right? So that means you can just play with this kind of crossover mutation operators to get the best architectures, or to generate the best architectures using because this parent is a kind of solution here. Again, this is parent 2 is a kind of a solution, and if we are just combining them together, we're getting another solution which is close to another popular architecture. So I mean, you will also find a lot of other interesting things, right, in the field of neural architecture search. So it is a bit difficult, a bit complex, but very motivative and very interesting as well. There are a lot of work still left in this field, right? So multi-objective, because it is mostly considered as a multi-objective optimization problem. So many multi-objective optimization problems or optimizations can be explored here, and it is mostly applied to the convolutional neural network. But for the last 2-3 years, people are focusing on some other types of architectures like transformers or convolutional transformers, which is having even more capability than the traditional convolutional neural network, because this convolutional neural network is very good at extraction of the local features, but not good at extraction of the global features, which are very important in some applications. And this convolutional neural network will give us this convolutional transformer will give us the idea, or you can say they give us the idea, or will give us, or will help us in extracting both local and global features. So those kind of architectures can also be, right, designed with the help of this neural or evolutionary based neural architecture search. I hope. Uh, yeah. So the time is 7:30. Yeah. Shall I continue, or I finished actually. So can I continue for 1-2 minutes?
Yeah, No problem. You can
Okay.
continue.
Okay, sir. Thank you so much. I think there are also, I mean, if you just go through the literature, you will also find the applications of metaheuristic techniques in optimizing the parameters of the neural network, right? So there's a lot of works that have been proposed over the years. And if I just, we have also, similarly, we have also done few works, right, a couple of years ago, that how to design some algorithms, or how to enhance some of the existing algorithms, and how to apply to update the parameters of the convolutional neural network. So mostly we have designed, a modified sine cosine algorithm, which is the only one algorithm based on trigonometric functions, right? So that's why it caught our attention at that time. So then we have found that it is having some issues, and so we have introduced just a mutation operator into it, which will give us the additional diversity, right? And also we have found out that it is giving better result compared to the traditional ACA. So this is the whole algorithm, right? If you just go through our paper, you will I'll just keep the algorithms and all, how we have introduced and what are the possible things we have done. So I just want to showcase some results which we have obtained, right? How to just update the parameters. It's a very common problem, I know. That's why I've kept it at the end of my lecture, right? It's a very common problem, but the kind of architecture which we have chosen to update the parameters is a extreme learning machine and a random vector functional linked neural network, which are nothing but known as a single layer feed forward neural network, where it's a three-step procedure only. So it is also free from this gradient descent approach and all, right? But because here there are only two layers, as I said, there are two layers, means there is only one hidden layer. So there will be connections only from input to hidden and from hidden to output. So input to hiddens are usually taken in extreme learning machines randomly, and these particular hidden to output weights are most important one. And this has been computed with the help of analytical approach. I mean, using pseudo inverse approach. Using this approach, you will just go through the paper. You will just easily get to know that what is extreme learning machine and how it is similar to this random vector functional link network and all, right? So whenever we are considering right, this input to the hidden weights as random values, so ultimately we end up with different results at different times, and at the same time you will also get an ill conditioned hidden layer output matrix. So to avoid this problem, we have just thought of applying some sort of optimization algorithms to optimize the weights from the input layers to the hidden weights. That was the idea. And these are how these solution vectors will look like. It contains all the weight values and the bias values that are involved in from the input layer to the hidden layer. And the kind of fitness functions which I've chosen is again the error values, right? And here is the fitness value and all, how we are selecting the S best and all, right? And finally what we are getting is these results, right? So you can see, just we have compared these results with so what I'm trying to showcase here is with less number of neurons we are getting better results compared to the other algorithms like differential evolution, PSO and all, and maybe some traditional approaches like extreme learning machine and supervision algorithm. Here are some other results on some other data sets, right? And finally, there are some future research directions, as I already told, that maybe we need to explore more um, the NSA algorithms like neural architecture, sorry, NAS, the neural architecture search over the advanced deep learning architectures like convolutional transformer and all. And we can also think of how to apply this multi-objective or analyze them or explore multi-objective optimization algorithms in an NAS problem, although it has been applied, but still there are a few works to be done in future. And here are some references from where I've taken the contents. Okay, so thank you very much for your patient listening. So if you are having any query, then you can just write it in the chat box. So I will try my best to answer. So I'm just so I've shared my email ID in the chat box. Those who want to connect or those who are having some doubts, they can also share their doubts over the email.
And
So
if you
I
have
think
any query, you can
hmm,
type it in the chat box.
I could not find any query in the chat box.
Yeah.
Yeah.
So thank you, Dr. Deepak, for giving such a nice elaborative session. You have covered several aspects on application of the optimization technique to design effective neural networks as well as to several image processing applications. So thank you. Please do share your slides. It will be passed on to the participants on
Sure,
the
sir.
course. So thank you very much.
Yeah. Thank you so much, sir. Thank you so much for the opportunity. Thank you.